So now we're moving into chapter 9, which is all about algebra. We spent most of the course so far looking at all sorts of different types of numbers, and now we get to put them into use. And you may be wondering, why are we doing algebra in a course about math for elementary teachers? Don't students not do algebra until 8th or ninth grade? Oh, um, formal algebra, yeah, is a class that students would take later, but the foundations of algebraic thinking really begin at the very beginning of their schooling. And we're going to talk about that in a moment. The different ways of algebraic thinking that are developed grade by grade. So let's go ahead and dive in and get started and look at what this first section of chapter 9 is all about. It's problem solving with algebra. The next section, 9.2, we'll get into graphing, but for now it's going to be problem solving with algebra. So here is for 9.1, our overview, our terminology. We're going to do a quick spotlight on teaching and learning. We'll talk about variables, algebraic expressions, equations. We'll be doing solving of those equations, talk about equivalent equations, properties of equality, and then we'll get into inequalities, which we also have to solve, talk about equivalencies, and then those properties of inequality. So I mentioned a minute ago, right, why do we have to do this for teaching for elementary students? Well, the thinking of algebra has to be developed before students learn formal algebra. Algebra isn't all just about X's and Y's and solving equations. It's about thinking a certain way. And the origins of algebra didn't involve any X's and Y's. It was all written out in language. And so in kindergarten, even, students start to develop the skills of algebraic thinking. Again, as you can see there, clap, clap, snap, using objects, fingers, mental images, drawing, sounds, all sorts of different things to represent mathematical ideas. Grade 1, as you can see, unknown addend problems. We talked about missing addends back, I think it was in our chapter about whole numbers, how you go about thinking about subtraction. It's not always just about starting with one number and taking something away. Sometimes it's about filling in the gap that's missing. That's algebraic thinking. Grades 2 and 3, you can see different things of algebraic thinking, working with equal groups of objects. You can start to write an equation using an equal sign. I like that example too about breaking sets of cubes into equal groups, and that's a way to tell if a number's even or odd. Those things are all, again, developing the foundation for algebraic thinking. Grade 3, unknown factor problems. That definitely is used in algebra. And grades 4 and 5, you can read those as well on your own. But as you can see, there are so many different foundational concepts for building good algebraic thinking, which is what really matters. Once you have developed those skills, putting them into practice in algebra class is a lot easier than if you're trying to develop those skills once you get to that class. So here's a problem opener that I'd like you to do. We will discuss this at the end of the final video for chapter section 9.1. It says a whole brick is balanced with with 1 pound. That weight is 1 pound and 3/4 of a brick. So what is the weight of the whole brick? Take a moment and see if you can figure that question out and then come back. I'm going to keep on going. So as I mentioned before, algebra as an idea was developed thousands of years ago. And it came from this document that was discovered, I think in the 1800s, called the Rind Papyrus. And the words that were used, again, were not X's and Y's, but they might have a question that says something like this: heap and 1/7 of heap is 19. What is a heap? Okay, so as you can see, there's no equation, there's no variable. It's just stated as a statement and a question. Today, we would represent that problem right there like this: H for heap, 1/7 of a heap is 19. And we would go through a process of mathematical algebraic manipulation to solve that. So we've really condensed the way it looks into what we now think of as algebra. But the idea of algebraic thinking and problem solving really comes down to this, right? Being able to interpret this sort of question. So what we'll do now is get into some of the terminology that we use in algebra and start solving some equations. So the first thing we'll do, I'm going to type some of this rather than write it. So let's define some things. The first thing we need to define is a variable. So often when you see that word variable, you think X or Y. But what it really is, it is a letter or symbol used to represent an unknown number. That's what a variable is. It's a letter or even a symbol that we use to represent an unknown number. Now, often in modern day algebra, we use X or we use Y, but in lower grades, it could be a square or a triangle that is used, because sometimes that can be a less intimidating than a letter. And so again, that problem we saw earlier with the heap, it said H plus 1/7 H is equal to 19. In that case, we're using H as our variable. It's the unknown thing because it says what is a heap. And so H is representing the value of the heap. In elementary schools, again, to represent an equation, we might say a square plus 7 is equal to 12. And then what is the value of the square? Again, it's a little less intimidating. Or you could even do a square plus a triangle is equal to 15 and have the students come up with all the different combinations of values that you could have for the square and the triangle. You could say the square is equal to 10 and the triangle is equal to 5, right? So it feels more like, again, less intimidating than just a straight up letter. Eventually we transition, right? We build the concept and then we transition into a slightly different scenario using the same thinking. Now we use operations. Again, operations are add, subtract, multiply, divide, when we want to indicate that a number is interacting with a variable. Again, a number and an unknown number. Variables are unknown numbers. They act like numbers. They behave like numbers because they are numbers. So if we want to indicate that 3 is being added to some unknown number, we would write 3 plus x. Or maybe there's subtraction going on. Maybe we have some unknown number and we're subtracting 5 from it. So we can write x minus 5. Maybe there is division going on. And so our unknown number is being divided by 4. We could write it with that division symbol, or more frequently as a fraction, because a fraction can also indicate division. With multiplication, we don't even usually use a symbol. There are a couple of different ways we can do it. But if we wanted to say that the number 6 is being multiplied by our unknown number, you could put 6 and then a dot and then your x. But what we do more frequently would be 6x just right next to each other. When we write that, that means 6 times whatever number x is. It's also important for us to remember what multiplication is. Multiplication is repeated addition. So when we write 6x or 6 times x, it means this. I mean, 1, 2, 3, 4, 5. That was a bad x. 5, 6. That's what 6x means. 6 times the unknown number means the unknown number was added 6 times together. That's how we do any multiplication. Multiplication means the number was added that many times. Another way we can do multiplication or represent it is with a set of parentheses. This will come in handy later, but this is going to be our most common way when we want to show multiplication with a variable. All of these things that we just did are called algebraic expressions. An expression containing symbols, right? A meaningful, let me write a definition down here for you. It's really a meaningful, hold on, let's spell it right. Meaningful combination of, and sometimes my keyboard goes crazy. Sorry. Let's go back, of numbers, variables, and or operations. Okay, so it's some combination of numbers and variables and operations: add, subtract, multiply, divide, exponents. Those are our algebraic operations. Returning to that question from the Rhind papyrus that I'm going to keep referencing, we had that statement that said h is equal to, h plus 1/7 h is equal to 19. This part right here, h plus 1/7 h, that would be an expression, an algebraic expression. The entire thing is an equation. And an equation is made up of expressions on both sides. So an expression, h plus 1/7 times h, there's your algebraic expression. One thing we can do with algebraic expressions is we can evaluate them. We can evaluate an expression. Evaluate means something different than solve. Evaluate has a very specific meaning. Right in the middle of the word evaluate, you'll see the word value. Evaluate means find the value of. And when you do that, you will come up with a final numerical answer. And so we might do this. Let's do it like this. So I'm going to instruct you to evaluate the following algebraic expressions for h equals 14. And here is our first algebraic expression, 15 plus 3h. First of all, notice that that's an expression. It's just a statement of numbers and operations and variables, okay? When we evaluate an expression, we substitute in a number for the variable. So we can say that this thing is now equal to 15 plus 3. And remember I said earlier we can use parentheses to show the multiplication. We are going to do that here because we're substituting in a number for that variable. Once we've done that, now we'll use the proper order of operations to find the actual value. So it would be 15 plus 3 times 14 is 42, and 15 plus 42 is 57. And so again, when we evaluate, we find the value of that expression. And in this case, it would be 57. You'll be given a value for that variable when you're asked to evaluate. Here's the other one we'll do. It is h plus 1/7 h. That looks familiar, right? And so again, what we'll do is take both of these h's and we will substitute in the number 14. 14 plus 1/7 of 14, or times 14. Hopefully you remember from our work with fractions that 1/7 times 14 means the same thing as 1/7 of 14. And when you do that little bit of multiplication, it can look like this: 14 over 7, or 14 divided by 7, which is 2. So we have 14 plus 2, which is equal to 16. So the value of this expression would be 16 if h is equal to 14. So let's go ahead and try these two on your own. So the first one says 4n minus 6. And if we remember that 4n means 4 times n, we would say for number 1, 4n minus 6 is equal to 4 times, and here we're given n equals 28 as our variable value. 4 times 28 minus 6. Remember that we would multiply these first. 4 times 28 is 112. Then we subtract our 6, and we get 106. For number 2, it says 3n divided by 12. We would do the same thing, substitute in the number 28 for our n. 3 times 28 divided by 12. 3 times 28 is, it looks like 60, 80, 74. No, 84. 60, 24. Yes, 84 divided by 12. Now we do our division, and 84 divided by 12 is 7. So that's the idea of evaluating an algebraic expression. You are given the value for the variable, you substitute it into the expression, and then you find that value. And one standard practice that we do is we often will work our, if we have room, we work our expression down, and we use equal signs, because our equal signs are indicating that whatever we had before is equal to what we have after. And as we're going through this process, what we're really doing is we're simplifying this as we go, right? We substituted it in at the very beginning, and then we're taking this expression and we're simplifying it. Simplify with each step. Simplify means you're replacing one expression with a new expression. Okay, so there's our expressions. Let's now talk about equations. So what is an equation? An equation is a statement that two expressions are equal. That's all an equation is. The sign we use, equal sign, means is or equals, right? So that's what our symbol means. And that's a really important thing for young people to learn. The equal sign is stating that whatever we have on both sides of that equal sign are equal to each other, okay? It means that they have the same value. What we've come, I think, in education, what we've often come to misinterpret that equal sign as, we start to think about it as compute this. If you pull out any calculator, just got my my iPhone calculator here, and if I do a computation on my calculator, in the bottom right-hand corner, there's a little button there. You can't see it. It's the equal sign. Can't see it, right? It's the equal sign. And so when we type something in our calculator, we hit the equal sign when we want to compute something. Any calculator, it's going to have that equal sign. But that's not really what our equal sign means in algebra. Our equal sign means that the things on both sides of it just have an equal value, right? They are equal to each other. It does not mean that one side is the answer or not, okay? It just means that the two things are equal to each other. And if we go back to that original equation that we looked at, h plus 1/7 h equals 19. One of the things we're going to do is solve the equation. And we're going to talk about what that means. So solve an equation. This has a very specific definition that's crucial for you to know. What it means is this: find the value of the variable. I'll even put s in parentheses because sometimes you can have more than one variable. We'll just say one for now. Find the value of the variable that makes the equation true. That's what it means to solve an equation. You're going to find the value of the variable that makes that equation true. Okay? Often when I ask that question in class, people say it means find the answer or do x, get it to x equals. And those are correct statements, but it's not really the heart of what it means to solve an equation. And this is going to matter for us, especially as we move through the rest of this chapter, even into the graphing section. What does graphing mean? It has to do with this definition. And so I'll just let that sort of sit with you for a little while. So the typical way that we solve equations is to whittle it down and sort of simplify the equation as we go, replacing the equation with a simpler version whose solutions are the same. And as we do that, what we get are equivalent equations. And so two equations that have the exact same solution are called equivalent equations. Here's a very simple example of what I mean by that. X plus 2 is equal to 5. We could probably all look at that and note that there's only one number that I could replace that x with that would make that a true statement. And it is the number 3. 3 plus 2 is equal to 5. X plus 1 is equal to 4. We could probably all agree that the only value I could replace x with and get a true statement with is 3. So those two equations we say are equivalent because they have the same solution. All right? One of the ways that we start the process of teaching and learning equations is through a balance scale model. We love models, we love illustrations that demonstrate the concept. And so what you're going to see here and what you'll have to do along the way is connect an equation with a balance scale, because a balance scale shows that the things on both sides of that triangle, right, that fulcrum there, that they are balanced. It means they have the exact same weight. What this balance scale here is illustrating is this statement: 3 of those little balls plus 5 of those little balls is equal to 8 of those little balls. And we can all recognize that that is a true statement. 3 plus 5 does equal to 8. Here we just have the sum listed, and here we have the total once you've conducted or completed that sum. So that's a great way to start the process. Now, we could also all recognize, I think, that if we eliminated one ball from the left side, we would have to eliminate a ball from the right side in order to keep them balanced. That would then say 2 plus 5 is equal to 7. And so that's the key when you're working with this balance scale model. Whatever you do on one side, you have to do to the other side. If you're going to take something off one side, you have to take it off the other side. If you're going to add something to both sides, right, then it's going to stay equal. And so that's going to be the thinking as we go through this process. What we eventually evolve to is something that looks like this. And in this case, you're going to see that we have some of those balls on the left, 5 of them to be exact. But then we have this little block, right, which we can represent with a square, or we could represent with an X. I'll just use a square for now. But that equals, if you count those, you'll see that there are 11 balls on the right. And so how would we go about finding how big that block is? That's really the question, right? It's also thought of as What number must be added to 5 to equal 11? There's that concept that I mentioned earlier. It's the missing addend. Subtraction, remember, can be thought of as the missing addend. What number do we have to add to 5 to get to 11? So this illustrates a subtraction problem of 11 minus 5. That's another way to imagine this statement. And so again, we think of the box as like hiding or taking the place of the number of those little balls that you would need in order to balance the scale. So how might we do it? Well, we might say, all right, if I need to find out how big this box is, I'm going to remove 5 of those balls from the left, which means I have to remove 5 of them from the right. And that's the same thing as doing 11 minus those 5. When we've done that, we now get a picture that looks like this. And we can see that then one of those boxes must be equal to 6 of those little balls. Okay? Now, what we have transitioned to over the years is a process that looks like this. If we start with 5 plus x equals 11, what we often do is say we're going to take 5 away from both sides. Some people write the minus 5 there. I always like to, even when I'm first teaching algebra to my students, like say draw a line down your equal sign, because there's your balance, right? There's the balance point. And so whatever you're going to do on one side of the line, you have to do on the other side of the line. I think that visual often helps students as well. 5 minus 5 is 0, so we've taken those 5 balls away from the left. And then 11 minus 5 is 6, and what we're left with is x is equal to 6. And this is, again, our simplified equivalent equation. So let's do a little bit more challenging of a problem. So the first thing I'm going to do is I'm going to write down the equation we're going to solve. 7x plus 2 is equal to 3x plus 10. And the first thing I want you to do is see if you can sketch out what a balance scale model might look like. Take a moment to do that. So what we're going to get when we do that is something that looks like this. We have 7 of those boxes. When we write 7x, it means you've got 7 of the unknown figures, of the unknown numbers. And those things are going to be added to 2. So those 2 of those balls is equal to 3 of the unknown boxes plus 10. And so that's the equation that we started with. Now, one of the things you're going to have to do in this class is learn about, in a moment, I'll teach you these different properties that allow us to do things to both equations. And every time you do a step, you're going to have to be able to indicate, what have we done? What property have we used? Are we just simplifying something? Or maybe we've used the distributive property, like we learned in previous chapters. So as we go through each step, it's important to be able to indicate, what did we actually do? For now, we're just going to keep using the boxes and chips model. So the first thing we would do is remove 2 of those. Actually, you can do this in different order. I'm actually going to do it slightly differently. You can choose to deal with the balls or the boxes first. It doesn't really matter. Just to keep consistent with what is on the slides, if you're following along on that, it would be removing 3 boxes from each side. So if we cross off 3 from the right, we're going to have to cross off 3 from the left. So what do we then get in our equation? So if we start with 7x plus 2 equals 3x plus 10, what we've done is we've taken 7x plus 2, I'm going to use a different color, we've now subtracted 3x from that left side, And then we had 3x plus 10 on the right, and we've also subtracted 3x from the right side. Now, some people like to write them in a line like this. Other times, people will do what I did earlier and write it right beneath. Either way is fine. Whatever way works for you is fine with me. When we clean up or simplify our equation now, what we're left with on the left, you can see from the drawing, is 4 of these boxes. 4x plus 2 balls is equal to none of the boxes, and we just have 10 of the balls. What's happened here is this 3x subtracts this 3x to leave us with 0 of those boxes, 0 of the x's left on the right side. On the left-hand side, we had 7 of those x's, and we subtracted 3 of them to leave us with only those 4. That's what the picture looks like. Here's what the process looks like algebraically. Then what we'll do is we will eliminate 2 of the balls from the right side. So we'll take away those 2. If we are going to write it out algebraically, we would write 4x plus 2, and then we would subtract 2, and that's equal to 10, and then we would also subtract 2 from the right. Just like before, we are subtracting those 2, and all we're left with is 4x, the 4 boxes on the left, and that's equal to, on the right, we're just going to have 8. So just to connect it back with our pictures, the first thing we did, again, was subtract 3 boxes from both sides, which left us like with something like that. And now we remove 2 balls from both sides, and we're left with something that looks like this. So here's where we're going to just pause and slow down a little bit, because now we introduce a different operation. And that operation is going to be division. Because we have 1, 2, 3, 4 of those boxes on the left, we are going to have to figure out how many would be in each box to balance this right side. So one thing we're going to do is, or way we can think about this, is taking the balls on the right and putting them into 4 different groups. That's one way for us to illustrate this and say how many are in each group. And we can see that if we segment them into 4 different groups, 1 for each of the boxes, each group is going to have 2 balls in it. Each box has 2 balls in it. What are we actually doing? We're doing division. So in this case, we are dividing both sides of our equation by 4. When we do that, we end up with x is equal to 2. Again, we've ended up with an image of our scale that looks like that. Each box has to have 2 balls in it for this to be balanced. So our solution then is 2. And I want to take a moment and just revisit what the definition of solve was. We were solving an equation. Do you remember what the definition was? It was find the value of the variable that makes the equation true. So what we should do then is check to make sure that our solution is actually a solution. The original equation was 7x plus 2 is equal to 3x plus 10. So how do we check to make sure that this actually is a solution? We substitute that value into our equation and then evaluate. 7 times 2 plus 2 must equal 3 times 2 plus 10. We need to evaluate both expressions. Remember how we worked on evaluating earlier? We're going to evaluate both expressions and make sure that they're equal. 7 times 2 is 14, and 14 plus 2 is 16. On the right, 3 times 2 is 6, and 6 plus 10 is 16. There's an equal sign between them. And so what we hope we end up with here is a statement of equality, that those two expressions are equal. And we did. That means it is a true statement. And if it's true, then it means it is a solution. What we've demonstrated through this process here are certain properties of equality. When we add or subtract things from both sides, or when if we divide or even multiply on both sides, what we've done is kept our balance scale balanced. And so there are three methods for obtaining these equivalent equations. Remember, we said equivalent equations have the same solution. This equation that we started with is equivalent to this equation. That equation is equivalent to this equation. And that equation is equivalent to this equation. Your solution is actually an equation. It says x is equal to 2. All four of those are equivalent equations. And as long as we follow these three properties of equality, then we're always going to keep our equations equivalent. So what are these properties of equality? They are these. The first one is the addition or subtraction property of equality. And what it says is add the same number or subtract the same number from both sides of an equation. So if you're adding or subtracting, you're using the addition or the subtraction property of equality. Multiply or divide both sides of an equation by the same non-zero number. That's the multiplication or the division property of equality. So again, we did that in that previous example. And then every time we do one of those, we simplify the equation and we replace it with an expression. We replace an expression in an equation by an equivalent expression. That's what we were doing here. We simplified this to get that. We simplified this to get that. So that's the process of simplification. The first thing we did was the subtraction property of equality because we subtracted from both sides. And then we did that subtraction property of equality again. And then here we did the division property of equality. And again, each time we also simplified from one property down to that next equation. And so that's how we solve equations, by using those four properties and simplification. And so what we're going to do is we're going to set the balance scale aside, or we'll sort of use the idea as we go, but we're going to now solve this equation. 5x minus 9 is equal to 2x plus 15. And what I'd like you to do is solve the equation, but as you do it, sketch a balance scale alongside it so you can, again, develop that modeling process. And then also see if you can indicate with every single step that you do, what property or process did you use along the way? And so take a moment, again, see if you can do that. See if you can do that process. So if you sketch this, again, it can be a nice crude sketch, right? Your balance scale might look something like that. And what you might have sketched is 5x. Now, 5 boxes. 1, 2, 3, 4, 5. Now, what you might even be wondering is, how do we sketch a minus 9? Because on the other balance scales, it was all plus. Well, we can do this a number of ways, and how you choose to do it is up to you. If you recall from a previous chapter on integers, we used black and red chips to indicate positive and negative numbers. So one thing you could do is circles and shaded in circles to indicate positive or negative. Or another thing you could do is make circles with pluses and minuses in them. So we could do 1, 2, 3, 4, 5, 6, 7, 8, 9. And because they're negatives, I might go through and just indicate that these are all negative. Maybe I'll put little minus signs in those. And then on the other side of the scale, I could draw my two boxes, 1, 2, and then I could draw my 15 circles, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then you could indicate those with the little plus signs in between them. Again, this elevates our thinking just a little bit because we have to work with both positive and negative numbers now. Or again, you could use different colors, you could use shaded and open. It's really up to you. And so the first thing that we'll do, that I'm going to do here, is I'm going to eliminate these two boxes from the left and these two boxes from the right, and that is going to be subtracting 2x from both sides. So what was my property that I use? That's the subtraction property of equality. Subtraction property of equality. Again, this is going to be important for you to be able to state what thing you're doing as you go. The next thing we do is we take this part and we simplify it. So when we simplify it, we get 3x minus 9 is equal to 15. So that was simplify. The next thing we're going to do is we need to eliminate these negative circles. How do we eliminate negative circles? You got to balance them out by turning them into 0. The only way to do that, if you recall back from our red and black chips conversation with integers, is to balance them out with positives. And so what we would do here is we would take 1, 2, 3, 4, 5, 6, 7, 8, 9 circles, and we have to add 9 positive circles. So I'm going to put 9 positive circles on my balance scale. When I do that, it cancels all of these out on the left-hand side. That's how they cancel out to be 0. We would then have to do the same thing over here on the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. And those are all going to be those positive circles. So I'm adding 9 positive circles to both sides. What does that look like in our equation? Plus 9, plus 9. What's the property that we used? The addition property of equality. Because we were adding to both sides. What do we do now? We simplify. We simplify both sides. When we do that, we're going to get 3x is equal to 24. Now, all we have left in our diagram here are these 3 little boxes on the left, and then we have 24 circles on the right. And so what do we do now? Well, if we want to find how much is in each of those boxes, we're going to have to segment this into 3 equal sections. And if we do that, what we're going to have would be 8 circles and 8 circles and 8 circles. 8 positive circles. What are we doing? We are dividing both sides of our equation by 3, which is the division property of equality. And then the last thing we do is we're going to simplify. X is equal to 8. So again, our steps were use the subtraction property of equality and then simplify. Then use the addition property of equality and then simplify. I'm sorry, addition property of equality, then simplify. Then the division property of equality, and then we end by simplifying. So it's really a 6-step process. And if we take our solution, x is equal to 8, and we substitute it back in here, 5 times 8 minus 9, and we substitute it back in here, 2 times 8 plus 15, and we check it, we will find out that both sides do end up equaling 31, and we do have a good solution. So that's our process. That's our process. So we're going to end this with one final problem. And it's not by giving you an exact equation. It's more, how might we problem solve? How might we start the process of problem solving with algebra? And so here's a question. It says, Eleanor wins the jackpot in a marble game and doubles her number of marbles. If later she wins 55 more marbles, bringing her total to 127, how many marbles did she have at the beginning? This is a problem that can be solved by creating an equation, but we're not going to do that because, when you're teaching this to students, they're not going to probably be ready to jump right into creating an equation. And if you think back to chapter 1, all our problem solving strategies, one of them was just guess and check. Sometimes you can just guess and check things, but as we do it, it's important to think about how we're going to organize our information. And so what you can do is create a guess and check table. And what that's going to look like is something like this, where you're organizing your process and your steps and your information. And so we say, okay, what if, let's just guess and say, what if she had 10 marbles to start? What would that mean? Well, if the first thing it says was that she doubled her marbles, 2 times 10, that would give her 20 marbles. And then later she won 55 more, we would add 55 to that 20 and get 75. And it said it brought her total to 127. Well, if her actual total is 127 and we got 75, 75 is too small. It's less than 127. So what does that mean? It means that 10 was too small. Okay, so that's what a guess and check process might look like. So what do? Well, we guess something bigger. So maybe we guess 40. Well, if we guess 40 marbles, as you can see here on the left, if we double those marbles, well, now she's got 80, and then we add the 55, she's got 135. That's too big. So 40 is too big. So this is what the guess and check method might start by looking. But the crucial thing is that we lay out for students, how are they going to organize their information? And making tables with clear descriptions and processes is kind of the key. How many marbles do you have? What are you doing in this step? What did you do here? What does this represent? Okay. And so we can then transition that to algebraic thinking, because the number that we're guessing here is our unknown number. It's our variable, right? It's our variable. And so maybe we can now evolve the process to look like this. If the number of marbles that we're trying to solve is represented by the letter M, and we double that, and then we add 55, we know that this statement here has to be equal to 127. And then we've created an equation that is going to help us solve this problem. Many students, when they just read a paragraph like this, they have no idea how to create an equation that models the scenario. That's hard. And so you start by saying, well, what if the answer was this, right? You guess and check, and then you start to notice a pattern. You start to notice a pattern evolve of what am I doing every single time? And that eventually leads you to this equation. So go ahead and take a moment and solve that equation just for practice. So the first thing that you would do, picture your balance scales. We only have boxes on the left. We got marbles on both sides. So we'd subtract 55 from both sides, leaving us with 2m is equal to 72. We use the subtraction property of equality, and then we simplified. Now we're going to use the division property of equality and simplify to get m is equal to 36. We can then, of course, go back to the table that we created at the very beginning, check, and see if you start with 36, double it, add 55, you get 127. So this is how the process starts of being given a scenario that you need to use algebra to solve. Algebra is powerful for solving problems, but it's not as easy as just make up the equation. You've got to start with the process, and then eventually that evolves to that building of the equation.